Ever wondered how airplane wings handle turbulence without shaking apart? Today we're breaking down the science behind wing flexibility using a three-mass model. We are modeling this wing that is shown in figure A as a cantilever beam, figure B, with three lumped masses. Think of it like a diving board with weights at equal intervals. Our goal, two things. One, find the flexibility matrix. That's how much the wing bends under force. Two, derive the equations that predict its motion, all while assuming uniform material properties and a fixed route. Now here's the secret. We're given the wing is modeled as a cantilever beam with three lumped masses M1, M2, M3 at distances L, 2L, 3L from the fixed end root. All segments have the same cross-sectional area A, flexural rigidity EI, and the length L. Now we're using the deflection formulas from strength of materials for a cantilever beam and a point load F, which are provided as shown. Now, the flexibility matrix relates the displacements at mass locations to the applied forces. Each entry, alpha ij, represents the displacement of mass I due to a uniform at mass j. Now let's test the wing. First, we apply a unit load at M1 and see how each mass moves. So at M1 itself, the deflection is L cubed over 3EI, like pressing a spring and watching it compress. At M2, um, we have a bigger bend, that is a 5L cubed over 6I. And finally, at M3, it's also slightly bigger. We get 4L cubed over 3I. This gives us a first column of our flexibility map. Now let's push at M2 instead. Thanks to Maxwell's reciprocity theorem, we already know M1's deflection matches M2's from case 1 because of the physics that is beautifully symmetric. So at M2 itself, we use the deflection formula for segment BC with F equals to 1, X equals to 2L, and alpha equals to 2L also, and we get a stiffer E8 is equals to L cubed over 3EI. Now at M3, we have a whopping 14 L cubed over 3EI, showing forces amplify toward the tip. Finally, loading the tip M3, M1 and M2 deflections mirror previous results as expected because the reciprocity saves us work. And at M3, a massive 9 L cubed over EI. The wing bends easiest here. Now we've got all the 9 terms of our flexibility matrix. The next step is to derive the equations of motion, and the equations of motion for the system can be written in terms of the flexibility matrix or the stiffness matrix. Now the stiffness matrix is the inverse of the flexibility matrix. However, for equations of motion, we can directly use the flexibility form. The mass matrix, M, since the masses are lumped and uncoupled, that is how we get the mass matrix. Notice the symmetry, and that is an indication of how reciprocity works. Now, for the equations of motion in flexibility form, the dynamic equilibrium in terms of flexibility is found using Newton's second law. We get flexibility multiplied by mass times acceleration plus displacement is equals to 0. So this elegant equation allows engineers to predict vibrations and design wings that survive storms. So substituting alpha and m, this is what we end up having. So the flexibility matrix is derived by applying unit forces and calculating displacement using beam deflection formulas. The equations of motions are expressed in terms of the flexibility matrix and mass matrix, presenting a generalized eigenvalue problem for natural frequencies and mode shapes. The system is a classic example of a lumped parameter model for continuous structures like wings or beams.